Is this not working?
No.
Yes, no?
No.
Irgendwie lässt er mir nicht zu. Es steht gesamten Bildschirm teilen. Zoom möchte den Inhalt des Bildschirms teilen und ich klicke auf Teilen und es geht nicht. Das Ganze ist inaktiviert. Also abbrechen ist möglich, teilen ist dann irgendwie nicht klickbar.
Ja, wir könnten auch so machen, wenn du mir die Folien schickst, dann teile ich und du redest dazu. Also ich würde die Folien weiterklicken.
Ich probiere noch einmal bei Application. Chrome. Ah!
Ja.
Perfekt.
Perfekt.
Okay.
Ja. Ja, ich werde jetzt anfangen, dich vorzustellen. Dann gebe ich dir das Wort. Möchtest du die Fragen während dem Vortrag haben oder am Ende gebündelt?
Ich habe so eine Endfolie, wo es steht Questions. Ich könnte aber auch, wie macht ihr das? Ich könnte nach jede Section sozusagen auch Fragen stellen lassen, sozusagen. Das geht auch.
Ja, ja.
Aber
also,
nicht.
Ja. Passt gut. Ich werde die Fragen dann sammeln über den Chat. Also du brauchst dich nicht um Chat kümmern oder irgendwelche Symbole.
Mhm.
Also so wie Handheben. Ich mache das. Und ja, wenn du dann mir das Zeichen gibst, dann werde ich die Fragen weiterleiten. Also ich werde das moderieren.
Warte mal, und wie gibst du mir das Zeichen? Ich sehe dich leider nicht.
Achso, wenn du mir sagst, so jetzt möchte ich Fragen beantworten. Also du steuerst das dann.
Wie ist es am besten? Was ist über die Tage dann jetzt, ist das rausgekommen? Was ist der Beste? Was würdest du recommenden?
Es hängt davon ab, ob du gerne quasi stoppst während dem Vortrag und auf Fragen eingehst oder ob du lieber quasi den Vortrag machst und dann alle 10 Minuten Fragen beantwortest.
Machen wir das dann alles am Ende.
Yes, okay.
Es ist praktischer jetzt.
Ja. Okay, ja, ich zeichne auf, aber frag dich dann um Erlaubnis, bevor ich die Aufnahme teile von deinem Vortrag und wenn du mir die Folien dann bei Gelegenheit schickst auch nachher.
Ja, genau. Das mache ich auch.
Okay, so let's start. Welcome everybody to our last lecture within our IEEE Signal Processing Seasonal School on Network Federated Learning. We have the great pleasure to have Diploma Engineer Anna Saranti from the Technical University Graz telling us about the problem or tackling the problem of bad explanations with the human in the loop principle. So just to give you some information about our lecturer today, Anna Saranti is currently, let me look it up, is currently a doctoral student at TU Graz in the group of Professor Dr. Andreas Holzinger. She obtained a master degree with distinction in computer science from TU Graz with a thesis on applying probabilistic graphical models and deep reinforcement learning in a learning-aware application. She is currently funded by an Austrian science funding project entitled A Reference Model of Explainable Artificial Intelligence for the Medical Domain. Sounds very interesting. Which is carried out also with the Medical University Graz. She has also been working teaching machine learning courses at TU Graz and TU Vienna, as well as the University of Applied Sciences in St. Pölten. And her excellent academic background is complemented by a broad experience as a software developer and data scientist in industry. So Anna, we are very happy to have you. Please take it away.
Thank you, Alex. Thank you for inviting me. I'm Anna Saranti, a PhD student of Professor Andreas Holzinger. He is now a full professor at the University of Life Sciences, the so-called BOKU in Vienna. And I'm really happy to be here with you in this federated learning school And the outline of my presentation is as follows. I will talk about explainable AI. I will talk about roughly what is a good explanation and what is a bad explanation. Those are not really not the most scientific terms. They are very subjective terms that I will use. But when we talk about good explanation, we think about explanations that make sense, that apply to us, that help us, makes us take decisions and make humans receive good actions. I will talk a little bit about graphs and graph neural networks, which are state-of-the-art neural networks at the time, and talk about explainability in those cases. And then I will talk about what our kind of research we're doing in our lab with the human in the loop principle. Why are we doing it? I will pass on to literature for all of you. And then in the end, I will accept all kinds of questions that you may have. Now, what is a good explanation? First of all, in the Medical University of Graz, we'll deal a lot with images of cancerous patients. And we would like to find out if an image of a cancerous tissue is cancerous or not, or how far cancerous is it. But let's assume that now that we have a binary classification task where we want to differentiate within images that contain parts with cancer and parts with not cancer. Is it cancerous or is the patient healthy? And images look roughly like the one on the left. We do have tissue. We do have also cells over the tissue. And we want neural networks to differentiate between those two. But in the end, we would like to tell the doctors about what parts were decisive for this differentiation between those two sets of images. And ideally, we would like to have explainable AI methods that tells us that those parts of an image contributed so that the neural network takes its decision and says, okay, this is cancerous and this part is actually non-cancerous. It doesn't tells us that this image is a cancerous image because, for example, the cells here are more connected to each other and have a particular structure, whereas here we see that the tissue doesn't have that kind of an organization, doesn't have that kind of a structure. But in the end, overall, the neural network has to decide, is it cancer or not? And those parts were more prevalent and win, for example, let's say, put it that way, and we can say that this is cancerous. One of the most important explainable AI method is called relevance propagation, which was invented and implemented in the Technical University of Berlin. Whereas after we've completely trained the neural network and we achieved convergence, we achieved the good metrics, we say, okay, we will do one forward pass and one backward pass of the relevance. Let's not mix it up with the backpropagation procedure of the training. The training is done. We've done with that. And then from the output, we compute the relevance of the output being the value of the output here, x of f, where f is the whole nonlinear function that's implemented by the neural network. And then we pass it back in the previous layer, and then in the previous layer, in a fashion, a mathematical fashion that is proportional to the weights of the connections. And in the end, ideally, we will get a heat map as an output where hopefully the parts of the cat that played the role to recognize this image as belonging to the class of the cat, having like the eyes and the ears playing the most significant role and the most positive role in this decision, and the background doesn't play a role and it's gray and didn't play a role in the classification. I will not go in this lecture about the mathematical basis of LRP, but I've already did YouTube videos about it, and there's also a paper that I'm going to refer to it about it with exercises, practical exercises about how can you compute this on paper and also implement stuff yourself. So I've explained whatever I could about the mathematical basis of LRP for people that are interested. Now I'm going to compare it to another heat mapping method because there's a lot of explainable AI methods out there, and they are also, I mean, every new neural network architecture will come with further explainable AI methods that explain that. And this is going to go, research is going to go forward by that. So the question is, what is a good heat map? What are good explanations? There's also sensitivity analysis, what one can compute, like the sensitivity of a pixel, for example, is the norm over all partial derivatives of the non-linear function that's implemented by the neural network. And it represents how much a small change in the pixel affects the prediction output of the neural network. So we could compute also that and not just use layer-wise relevance propagation, but we lose the direction of change because we use the norm there. And the result of this is that we have a heat map that we are not so happy with because, first of all, it has only positive values. We lose the information about parts of the image that speak against the predicted class. And more or less everything is either non-important or positively important, whereas on LLP one cannot see it probably here, but the shadows of the of those motorcycles here, for whatever reason that has to do with the discrimination process and what is the information in the other classes, played a role against the prediction, which is an information that it's very important to have, and we do have this with layer-wise relevance propagation. What is also positively with this method is that we can also, as data scientists, do whole data set analysis at one hand. So let's assume that we are software developers, we're data scientists, and we have a huge data set. We're talking about big data here, and we cannot possibly see every possible heat map on our data set. This would be an overkill for us to see if we are happy with our heat maps or not. So with an inspiration that was taken by a very important data set that was used in, I think that was a competition. I think it was a Kaggle competition that was used, the Pascal VOC 2007. They found out that all the horse images had a tag that's representative from the person that took the photos. And actually the high-performing neural network, I think it was a convolutional neural network, of course, then at the time, did pick that up and said, okay, whenever I see the tag, then there's a horse, which is actually mathematically legitimate. But in the end, when people saw the heat maps produced by LRP, they saw that this is not acceptable. This is considered like cheating to us as humans. And we don't want our neural networks to base their decisions on those kinds of artifacts. And there are also a lot of funny examples about this kind of different artifacts that one can find in data sets that neural networks pick it up. They call those clever hands predictions. And this all has to do with the fact that neural networks pick up correlations. And again, they do the work as they are trained. But the is that when you take and pick up an image which contains a car and put the tag, then the neural network says, okay, this is a horse, which is, of course, not acceptable. So what one can do is actually cluster the heat map images and don't see them. One doesn't have to see them all at once and spend a lot of time. And if we cluster the heat map, then we can see that for images being on the same class, one can have heat maps that concentrate the importance in different places and have a completely different distribution. And one would hope that, for example, outliers like those tags would be in clusters like that. And one could see, for example, there are different reasons for classifying something as a horse and pick that up because one would have a lot of different clusters from the heat map images and think that there are, in this case, for example, for the horse classification, four kind of like different reasons why a particular image is classified as a horse, and maybe this one is something that's an outlier, a reason that's like a tag or some artifacts in the outer part of the image, and pick that up a bit faster than all those heat maps one at a time. Layer-wise relevance propagation can be applied in other architectures as well, for example, in recurrent neural networks. Here I'm showing you an example of an LSTM and how perturbation analysis is working. An LSTM is trained in this example with sentiment dataset from Stanford. The dataset contains criticisms of movies that can be from very negative to very positive. It's a 5-class classification. And here you see examples of sentences that were classified as being very, very negative, like neither funny nor suspenseful nor particularly well drawn. These are criticisms of movies. And the upper part contains the result of sensitivity analysis for these sentences of this class. And here down, you see the results of layer-wise relevance propagation. And you see that although those sentences do have a negative sentiment, that sensitivity analysis don't differentiate between what is positive and what is negative content in this image. For example, funny isn't perceived by layer-wise relevance propagation as being negative because it works against the prediction of this class. Of course, neither funny is as a whole, and the whole sentence has a negative sentiment, but funny alone is not negative and speaks against this classification. For example, originality is something that is positive here. It's like it doesn't play a role at all. And or for example, mediocre is important in both cases. Thrilling is important by sensitivity analysis. We don't know in which direction this goes. So a layer-wise relevance propagation gives us much more information about the classification. And of course, the idea is to ask ourselves what will happen into the prediction if we remove important, positively and negatively important words. What will happen to the predictions of each of the sentences? Will I jump to the other class if I remove particular parts? And this is actually true. And they've compared sensitivity analysis and also random removal of words, and so that the words that are positively relevant, if one sorts them actually and removes the most positive, and then one removes the second most positive, and then one removes the third most positive, then the performance goes monotonically down, and LRP actually the LRP values and the sorting of those values gives us the most, I don't know, the most monotonical decrease of the performance. And the opposite goes for misclassification with increasing relevance. We see that if we remove the negative relevance values, then we do have increasing relevance. So LRP also helps us somehow answering the question of what can happen if I remove words that or parts of images that are mostly relevant or negatively relevant, how this will have an impact on the performance. And of course, this is also a very nice example to show how important layer-wise relevance propagation is and why positive and negative is important. Let's assume that we have a neural network that's trained to differentiate between images of cats and dogs, and we are happy with the performance, we're happy with the training, and then the neural network is confronted at test time with that kind of an image that we have a dog on the left and a cat on the right. So what speaks for or against the decision in that case, and what would a human do? Because LRP can say us that if the neural network is trained so that it says that this image overall contains a cat, then of course the parts of the cat played the most important role, and the parts of the dog irritate the network. The network is not so sure that this image is for sure a cat, and the opposite goes for the dog. But what would a human decide? What would the human say in that kind of a situation? And what will happen, for example, if we don't have enough images to train our neural network? What would happen if we don't have enough resources to train our network? What is the way to go if our neural network is not well enough performed or has an image that contains parts of the two classes after the training during test time, what are we going to do there? This is an example of state-of-the-art convolutional network that we used in a master thesis in the lab of ours. But we've used images that were easily to be accessed, open accessed in the internet, and we didn't expect a very good performance. And also our explanations were not so nice, and we were not so happy about those. Also picked up artifacts, and the question is, what are we going to do after that? And do humans trust AI when the prediction is wrong? Do humans trust the explanations if the performance of the neural network overall is not good, and the performance and I can say security, but the confidence by which the performance, the prediction is made is not good? How will that impact the explanations, and what can we do about it? So I'm going to jump now to graph data, although those are not very far away from images, because now nowadays we can process medical images by using, for example, packages like histocartography, which is implemented in Python, that returns us from medical images lots of information about the cells, like the centroids, texture features for each node. The graphs are usually extracted with configurable parameters, which have to do mostly, if I remember correctly, with distance between the nodes. And some of the most sophisticated of those, they create two types of graph. The upper part of the upper graph is graph of the cells, and the down graph is the graph of the tissue, and each cell lives in one of the graph tissue and belongs there. It's like a superpixel, the one that's underneath. And one can process those, and one can process images by graph neural networks that I will talk right now. And we can actually have not just 3 features at each node. We can not just have RGB on each pixel and on each node, but we can have any number of features, like I said before, like the centroids, like the size, the elasticity, ellipticity, the roundness, anything, convex, hull, perimeter. We can have information if this is convex or not convex, if the cells are convex or non-convex, and we can use that information, and we don't have to have the cells in an ordered way or the pixels in an ordered way to process them. And of course, the connections between the nodes can also have the features that, like I said before, distance or a particular weight, the importance of the connection in them, and so on and so forth. And of course, the neighborhood of a particular node plays a role in the processing, as I will talk about later. And for example, this is an image that of a protein structure that we are using, and the images process sequential and grid data, but we are nowadays want to work with graphical data, and medical images do contain graph data. One extracts the graphs out of them, but also biological data are inherently graph oriented, and biological data have this graph structure. Drug discovery also uses graphs, social networks, maps. Images can also be seen as graphs that have this organized structure, and also in between we do have reinforcement learning states that are also represented by graphs. And assuming that all of the students know how convolutional neural networks operate, in a similar way, graph neural networks work also. Like, in the same means that the convolutional network gathers information from the neighborhood of a pixel to update the value of a particular picture and learn the values of each of the filters that is going to be used. By the same means works a graph neural network by gathering information from the 1-hop neighborhood and the 2-hop neighborhood and so on and so forth to update the values that we have in the node, but maybe not 3, but maybe 10, maybe 100. And also this is one of an example of a graph that can be processed by a graph neural network and can contain completely different types of nodes and completely different types of edges. One can have drug nodes that are represented by 3 features, and we can have protein nodes that can be represented by another kind of features, because we need other other characteristics to describe those 2 biological structures which can be completely different. Hence, we can have heterogeneous graphs. They are of different type, they have different features. And one can also process multigraphs where many different edges of different type connect 2 nodes in a different type. Or one can also have the ability to connect with 1 edge more than 2 nodes, which is kind of difficult to imagine, at least for me. I hope that everyone is more or less okay with the mathematical description of graphs, describing nodes and edges. One can have, as I said before, completely different types of graphs: directed, undirected, simple, multi-relationals. One can have also self-loops in graphs, which I forgot to say. Usually we describe graphs with an adjacency matrix or the corresponding Laplacian matrix. And of course, there are numerous of libraries out there to process graphs. One of the most important ones that I use is the Python's Network X, which gives us the ability to compute very easily shortest path, the degrees of particular nodes. One can compute connected components and also visualize the graphs, which is also one of the most important things to do when one is confronted with a graph. The visualization we do usually with Matplotlib, but I also recommend PyVis and Bokeh, which is very convenient. And Bokeh also creates HTML output. And for visualizations of relevances on the edges and the nodes of the graphs is pretty convenient, because one can click on the legend and see only select particular nodes or paths of the graph to see only those, and be pretty selective and not have it cluttered one above the other. And to define the graphs, it's quite straightforward. One defines an empty graph, one adds nodes, adds edges, or one can use the out-of-the-box already typical structures like cycle graphs or star graphs, or even graphs with random connections like the Barabasi-Albert with those libraries. And to process them with graph neural networks, one doesn't have to do a lot, because there's a compatibility with Network X. And one can use the PyTorch geometric library or the DGL, which is based on PyTorch geometric. They have lots of nice tutorials, and one can convert from PyTorch to DGL, and I think also back. And also by the same means, we can transform them from Network X to PyTorch geometric. And the opposite, to visualize that then with a visualization package. And also those libraries do have a lot of benchmark datasets. One can download one big already created for us dataset for particular tasks, which I will talk about later. And one can have all kinds of functionality easy, like what is the size of the dataset, what is the number of features of the nodes, what's the number of classes, and one can play around with lots of interesting datasets with lots of different features for lots of different tasks. The graph representation in PyTorch geometric, since I am in a conference that's a bit also hands-on, is straightforward and uses internally matrices from NumPy, and one can say that a particular node contains values for its color, for its size, its shape. The second node also has its values. One can encode color, one can encode size, and then, of course, before one inputs it to a neural network, one has to process it to normalize it. And by the same means, one can define edge features like the weights, the distances by numbers, and encode this by numbers and use it as input to the neural network. Edges are also pretty straightforward to define. The node with index 0 is connected with the node with index 2, and so on and so forth. The targets are also easy to define. The first graph has the ground truth value of 0, and the third one has the ground truth value of 1. And of course, the position is important because one can visualize the graphs with different layouts, or perhaps one wants to position them in a particular way. And also additional attributes. We don't want the visualization of IDs. We would like to have some node labels. I would like to see, for example, that a protein has a particular name for our users. And to understand how graph neural networks process it, then we will use those features, which after processing usually are called embeddings, to update the values of a particular node based on the values of the features of its neighboring nodes. So this HA, HB, HC in this graph is, each of them is one row of this matrix. Okay. And this is repeated k times. The initial values of the features are replaced with new ones by gathering information from its neighborhood with a function which is represented by aggregate. I will come and say what is that, what can be this function later. But what is important is to know that to update the row of the features of the node A, one needs to aggregate information from the rows of features of node B, C, and D, and the same goes for B, the same goes for C. One sees the recursion here, so this is why I have the different color, or slightly different color. These are the values of the previous iteration, and so on and so forth. And of course, in the end, one has to combine it. An appropriate combine function can be learned by a multi-layer perceptron. One doesn't have to define it. One can also let the neural network pick up what are the optimal parameters there to do the differentiation, and what is an appropriate aggregate function. It can be a mean, it can be a max and a sum. Many people that have a background in Bayesian networks and probabilistic graphical models may remind themselves of belief propagation and conditional random fields. It's kind of like that. And of course, you can write your own module. You can define your own aggregate function. You can also create your own combine function with those packages. You can use already built-in aggregate and combine function by just calling the corresponding modules, and then also defining the architecture by that means, and also saying when you want to have the ReLU nonlinearity, the rectified linear unit, or some kind of other nonlinearity between your layers. And please don't take this as is. Use comments and formatting. I cannot put all the code in here in this page. Please look at the tutorials of PyTorch Geometric and DGL-AI, and yeah, be safe. What are the tasks that we can do with graph neural networks that implement that kind of a functionality? We can do node classification, link prediction, and graph classification at least. And of course, on the back of our heads is always, what will explainable AI methods compute? What will those return to us? Because for images, we've seen heat maps, at least heat maps, there are others, but let's concentrate on heat maps right now. For graphs, the result of an explainable AI method on a graph neural network, what will it return? One will assume that there are relevant subgraphs that are more important in the graph that will be highlighted, and the neural network will pick their characteristics to say, oh, this is a graph that has a particular belongs to a particular class, or walks in the graph, paths in the graph, and even causal structures are easy to be extracted. So the node classification task for information takes as an input as a graph, labels. The people have labeled some of the nodes, but the neural network wants to, or has to label the unlabeled ones, has to tell us what kind of label have those nodes that are not already classified, by taking the information about what the two classes of nodes, the red ones and the green ones, have, taken also information from their neighborhood, not them themselves. And graph classification is also related to node classification, because in the end, of course, the same or almost the same procedures are made in the graph neural network, and there is a combination of all the nodes embeddings in the end of the process to represent the whole graph, and then another graph that has a completely different structure. Of course, the methods passing and the neighborhoods are completely different. Thereby, the node embeddings of graphs of this structure will look different, and this will help the graph neural network differentiate between those kinds of two graph structures to take its decision and say this belongs to class 0 and this belongs to class 1. I will not go to many details about how the badge is working. There are two methods at least how one can do this, but I just want to show a visual about what the different structures of graphs might be. There's a great variability, and graph classification, one can consider it to be a quite difficult and very interesting task, because differentiating between all those completely different structures and topologies is pretty exciting. The graph isomorphism network is an architecture that I also have to refer to. And this is a very important architecture that differentiates between graph structure in the best and optimal way. This is made by Kevin Xu. He's a PhD student of Jure Leskovec. And this is one of the examples that they show of what is a good aggregate function and why mean and maximum doesn't help graph classification. In this example, one can see 3 sub-examples where this structure and this topology are not differentiated when one uses as an aggregate function the mean and the maximum, because this and this have the same mean and the same maximum, but the sum is completely different. So with mean and maximum as an aggregate function programmed, one will be able to do graph classification because they are quite the same. And similarly, for this 2 different topologies, the maximum of this and the maximum of that are also the same, regardless of the values that the features of the nodes will have. If they are the same in H1 is same with H1, the row is the same, then the mean and the maximum will not be able to differentiate between those 2 topologies. Same goes for C, because the mean of those 2 that are used to update this node, because they are in the immediate neighborhood, is also the same as the mean of those 4, which also consists of the neighborhood of H2. So the preferable aggregate function is the sum, and this architecture, the gene architecture, is representationally more powerful, and it's proven in the paper that it is as powerful as the Weisfeller-Lehmann graph isomorphism that differentiate between different graph topologies in an optimal way. Okay, let's see now 2 representative explanation methods for graph neural networks. The first one is the GNN explainer that computes the important subgraph of the computational graph, not the graph itself, by an optimizational algorithm, in the sense that it iteratively finds the substructure that maximizes the mutual information with respect to the prediction score. Again, we have the assumption that a subgraph exists that retains the predicted label distribution in a acceptable way, and with an optimization algorithm, an optimization procedure, we're trying to find this out. And in a very, very trivial, simple example, a colleague of mine, Dr. Bastian Pfeiffer, used it as the first to see how GNN explainer works, and then he implemented his own explainable AI procedures. He used 2 sets of Barabasi graphs that had in their nodes the same distribution of node features, and only one particular edge had a difference in the 2 sets, and this was picked up by the GNN explainer pretty straightforwardly, because this edge and actually basically the distribution of the values of the node features, if one wants to be a bit more precise, those were the differentiating parts that helped the graph neural network to separate those 2 classes. The PGM explainer perturbs the input graphs to uncover some dependencies and creates a lot of data. So one can perturb the graph and remove edges, add edges, and change perhaps also features of the nodes to see how the prediction of the neural network is, and then uses all those data to learn a Bayesian neural network. Sorry, a Bayesian network. There's no Bayesian. No, there is Bayesian neural networks. A Bayesian network from the generated data with structure and parameter learning, which is also implemented by PGMPy. It comes out of the box with PGMPy. This is also a Python library. And in the end, it computes conditional probability tables of the nodes that when their value is changed, so the distribution of the value is somehow defined by the data that were gathered during this experiment, is computed, and there's an estimation of the probability that a node epsilon has the predicted role with respect, for example, for node classification, given the realization, the values of the features of other nodes. So depending on the distribution of the values on the node A and the node B and the node C, and this structure of this Bayesian network, one can see what the distribution of the predictions of node epsilon would be. And what we saw from those two explainable AI methods is that they are both going towards a particular optimization goal and want to improve a particular metric and want to, so to speak, improve, for example, the estimated probabilities of the prediction. And there are always optimization methods inside of those software developments. But in the end, we know that neural networks will not have a perfect performance. We know that for this prediction, for example, might not also be correct. And since in the lab, Professor Hotziger also has a lot of years of research in the loop principle. Our question now is, how do we get out of that? What will happen if those methods, for example, regardless of what it is, do not deliver plausible relevance distribution? What will happen if we show to a doctor or a biologist a graph where there are relevances on edges and nodes that they're not in accordance with their own knowledge? What if the doctor or the biologist says, well, your neural network has a performance which is 90%. This prediction can be right with a particular certainty or not be right. And then the explanation method says, okay, this node is important or positively important. And the doctor says, no, that's not in accordance with my knowledge. What we will do then? And are all those explainable AI methods results plausible for them or not? So we gave the humans the ability to use the explainable AI methods also, but to somehow counteract on them if they don't make sense of them, if they are not in accordance with their knowledge, and see what happens with that kind of interaction from a UI platform that uses explainable AI methods, but also doesn't follow them blindly towards an optimization goal. So the users can upload graphs with the standard formats that I've said before that NetworkX, PyTorch geometric use, but they can also add, delete nodes and edges, add, delete features, and predict or retrain graph neural networks depending on what they want to do, use the explanation, and also give us feedback if they are happy with the explanation or not, in the sense of the causability principle, if they understand what the causal connections are between those changes that they initiate and the performance results of the graph neural network. They don't have to always pick up the most important node, the most relevant node. They don't have to pick up the most relevant edge, although we will present the most positively relevant and the most negatively relevant nodes and edges, as well as their neighborhood, so that they have an understanding first. But in the end, they're free to counteract that and say, okay, I will forget this because the prediction is not so high. They will also see what the performance will be, to have an idea how good the performance of the whole neural network is, and also how certain the neural network is about a particular performance, about a particular graph, sorry, about a particular prediction of a graph. And by that means, we can incorporate also human domain knowledge and don't forget this and go towards an optimization goal. So how do we imagine that predict and retrain will work? We know that the user will change, for example, 3 graphs, and the graph neural network cannot, it doesn't have to be retrained actually. And the predictions of those 3 graphs will change, and the relevance distribution of those 3 graphs will also change. And then the game begins again. Then the human decides again based on the new relevances. But assuming that the graphs are completely changed, they have a completely different number of features, or they have completely different characteristics and have a lot of changes. Let's assume that, for example, the similar corresponding thing happening to an image data set where lots of changes are made, then we expect that to give also the user the ability to change the graph neural network completely and retrain it, and also suggest the architecture of the graph neural network that is adequate for this task. The predictions of all of those, even the unchanged ones, will change, and the relevance distributions will also change. And this is also the end, how this will be actually the end UI part will look like, that how the modifications will be made, how will you use a particular, see a particular graph in a particular patient. I cannot show everything right now, but I'm going to be really happy to answer the questions afterwards. We will have a lot of humans to do this kind of experiments. We also have a causability lab where people as eyes and movements and also the things that we'll say will be also tracked to see how happy they are with the UI, how far they understand the explainable AI methods and the explanations that they will get, and in what sense they think that those explanations do make sense or do not make sense for them, and how far they listened and accepted the results of explainable AI methods, and how far they didn't and did something against it. So the literature for everyone, the main relevance propagation paper is from Montaron Gregoire. There's also a great page at the Technical University of Berlin that has a lot of examples also from the industry about the application of layer-based relevance propagation methods. There's also a practical tutorial on several explainable AI techniques, which I took part also with Andrian Beneteau and Professor Natalia Rodriguez, which is mostly for students that want to see how explainable AI methods work. And also we do have also, I think, Jupyter notebooks. Yes, we did it last year for people that also need to take pencil and paper and compute relevances on simple neural networks. I highly encourage every student to do so before they start Python programming or using the Investigate toolbox for layer-based relevance propagation or something that's already implemented, to see how the inputs and the outputs and the weights, also the juxtaposition of different weights help a particular prediction, and then the relevance computation in the backward pass. The differences with sensitivity analysis are also very good analyzed from all the people that are in the research group of the Technical University of Berlin. A lot of images in those two papers to see visually the difference in quality in explainable AI methods. The graph datasets Open Graph Benchmark has also a very nice paper about the different characteristics and variations that you can find in graphs. For the most traditional folks, graph neural networks books, there's one for William Hamilton and one which is free about geometric deep learning, which is, at least for me, a little bit more difficult. I think this one is one of the first, and there's also others that are going to come up. 3 important papers about different graph neural network architectures, Ku, Lu, Xu, about the difference between the graph neural network architectures as far as graph classification and the difference between the different aggregate functions and the representation power. And also one for the more theoretical inclined from Lucas Andreas, what graph neural networks cannot learn, depth vs width, what are the representational limits and the discrimination and differentiation limits between different graph neural network architectures. And for explainable AI on GNNs, the GNN explainer paper, the PGM explainer paper, and of course, a new paper from the group of layer-wise relevance propagation from the TU Berlin about applying LRP on graph neural networks under particular constraints. Highly recommended too. And I'm happy to hear your questions. And also feel free to contact me per email for questions in my email at the Medical University of Graz. Thank you very much.
Thanks a lot, Anna, for this brilliant lecture about the state of the art in explainable AI and applications to medical sciences. So here are a few questions on the chat. The first one, can you use LRP also for regression tasks?
Regression task implemented with neural networks? Yes.
Yeah. So I guess
the constraints in the layer-wise relevance propagation are not in the task that one can do. The constraints are in the architecture of the neural network. In particular for the graph neural networks, for example, there have to be it's in the paper, there are 3 constraints, at least that I can remember from the graph neural networks perspective. Same goes for some fully connected neural network architectures. Also very important to say about some convolutional network architectures that have connections backwards and forwards, like the ResNet, for example. One has to do some type of unrolling on them to apply LRP. One cannot do that out of the box. One cannot take a ResNet and apply LRP on that out of the box. One has to change the architecture a little bit to apply this, but it's possible.
Okay. Then the next question, can LRP used also for time series data, or did you see these applications to time series data?
Yes, yes. Actually, this is since LSTM is processing sequential data and time series data. Yes, it is possible, again, with the constraints that are in the paper of Leila Aras. This one, for example, this used an LSTM on text, but the same LSTMs with this particular architecture can be used for time series data or any type of sequential data. And then in the end, one can apply LRP and perturbation analysis too. One can remove stuff and see how the performance is changed. Thanks.
And then another question is, or are you aware of connections between LRP and the attention mechanisms? Is this somehow related to attention mechanisms?
Yes, it is true, but I haven't read the paper yet. There was one, I think at the beginning of 2021, when they also used and compared it with attention mechanism, but it's not. Well, if I have to include this in my presentations in the future, I might do that. Yes.
Yeah. Thanks a lot. Yeah, then please, everybody in the audience, go ahead with posting other questions on the chat. In the meanwhile, I would be interested in, as I understood, you evaluate the quality of explanations using studies, user studies.
Yes.
And how, I mean, ideally, the coolest thing would be if you can read from the eye movement how the user perceived the explanation, and just from looking at the eyes, finding out this was a good explanation or not. But how are you doing it currently? If you could remind me about this.
Oh, I've been in the causability lab once, and this is a work that's actually done from my colleague, the master student Alessa Angeschmidt. Mm-hmm. She's the responsible for that. So I don't know if you want to have another lecture about this and how we're doing it, then I'm happy to do so. But we do have this. I think I don't know if it's from Google or I mean, I don't know how to describe this, but basically the people have this huge thing on their face, and this is like a glass, and we do track their eye movements and what they're doing and where they're looking at. And I've seen that in the causability lab when people see videos of games, how this really works, and where people actually are looking when in the game a person walks into a room or something explodes, how easily it is to track the eye movements. Yes, but we don't want to so much to leave it on the eye movements. This is the first thing, and it's a very important thing, but it's very important to also record the whole thing. We are really, really interested to see the reactions, the words that the doctors would say, but because doctors, they see the heat map, they talk. And when they make a diagnosis, they write stuff. So they talk a lot, they write a lot, they're not just looking. So we would like also to record what are the immediate interactions, if they're happy or if they're not happy, if it does make sense or it doesn't make sense.
So. Are you aware of recent papers on that study exactly how explainable AI works in medicine? So how this helps, supports the doctors. Are you aware of recent publications on this or larger studies?
This on what particular topic? This is a very general topic. There's a lot of surveys that come out and say, okay, how explainable AI is used in medicine one. But I think, can we like pinpoint that a little bit more about how they're helping, how the performance is compared, or how the acceptance is increased, or dealing with trust, or dealing with what is this is a, Alexander, do you know what I mean? This is a very broad thing.
I mean, ultimately, when it comes to health, I'm interested in the end to get good treatment. So somehow measure if the explainable AI techniques improve the diagnosis quality, something like this.
Quality.
Yeah.
Not out of the box. I think that there is one paper that, again, the Technical University of Berlin group did in 2019, and I can also refer to that, where they saw exactly how LRP is used and how people, how doctors use LRP to see the heat maps and take decisions from the heat map and see stuff and say, oh, this is cancerous or not cancerous. The thing is this, that, okay, we do have the results and we do have the explainable AI heat maps, but in the end, it's the doctor that will decide. So it's not like we do create a neural network that gives us a performance, and we do have the explainable AI method, and then we leave that, and we do have a diagnosis. In the end, there's a doctor that will say if he or she will use that for his own diagnosis or her own diagnosis or not.
Yep. Okay, that's a very exciting topic. Thanks a lot again for your excellent lecture, Anna. It was really a great pleasure to have you. And yeah, I'm looking forward to some potential follow-up collaboration. We have quite some common interests. And yes, to the participants, please do not hesitate to reach out to Anna by email. You find her contact on the school site. And I will also share, if you agree, Anna, I will share the recording with participants.
Absolutely.
And if you could also, if not already done, share the slides with me so I can forward them also to the participants.
Okay. Great.
Thanks a lot, Anna, and have a nice day.
Thank you. Bye.
Bye.